Hello, welcome to today's session of organic chemistry. In today's session, we'll be talking about these three important factors which affect the stability of reaction intermediates in organic chemistry. When I say reaction intermediates, I'm talking about the carbocations, carbanions, and free radicals. Before getting into the details of those factors, let me do a little recap of what we have covered so far. In our first session in organic chemistry, we talked about the three important chemical reactions. We talked about free radical substitution reaction in alkanes in pretty detail. We talked about the mechanism, the steps involved, and the products. We also talked about the electrophilic addition reaction in alkenes and alkynes, mainly in alkenes. We talked about the three different pathways that the electrophilic addition reaction in alkenes goes through: the carbocation pathway, the halonium ion formation pathway, and the concerted addition pathway. And we'll talk about the nucleophilic substitution reaction in the future. And after that, we talked about the three different reactive intermediates that we encounter in organic chemistry, mainly the carbocations, carbanions, and free radicals. Okay, so now let's talk about these three important factors that will determine whether one carbocation is more stable than the other, or one carbanion is more or less stable than the other, or one free radical is more or less stable than the other, right? These three important factors are: first, hyperconjugation; second, inductive effect; and three, resonance effect. Okay, and we'll talk about the details of these three effects in our next few slides. But before getting into these nitty-gritty details, I want you to keep this in mind. Okay, what we are trying to see is whether these three factors are concentrating the charge, which means making the carbocation more positive, making the carbanion more negative, making the free radical more electron deficient, whether these factors are contributing to the concentration of charge, which means that they are making the carbocation, carbanion, or free radical more destable. Concentration of charge will lead to destability. Or whether these three factors are diluting the charge, delocalizing the charge, dispersing the charge, which means they are making the carbocation, carbanion, and free radical more stability. Just keep this in mind. Concentration of charge, enhancement of charge will lead to destabilization, making it more reactive, and dilution, delocalization, and dispersion of charge will lead to stability by making it less reactive. Okay? So the first factor is hyperconjugation. The name sounds pretty fancy, but it's a very easy concept once you learn this. Okay? So if you see the picture on top, before we get into the definition, I want you to see the picture. So I have a picture of a methyl ethyl carbocation. So if you see a picture of carbocation at this point, from now onwards, there should be few things that should come into your mind. Okay, first, there is a carbon with a positive charge, and the geometry of that carbon is trigonal planar because it's going to have 3 electron domains around it. That means it's also going to have an empty p orbital, right, which is ready to take an electron. And because of this carbocation behaves as an electrophile, electron-loving group. And unless it's a methyl carbocation, there are always going to be some CH bonds surrounding that positive center. So, for example, in this ethyl carbocation, surrounding this positively charged carbon center, there are 3 CH bonds. And there could be more, depending on whether it's a primary, secondary, or tertiary carbocation, right? And those factors are really important to understand hyperconjugation. So now let's look at the definition. Hyperconjugation is a stabilizing interaction that results from the interaction of electron in a sigma bond, CH or CC, both of these are sigma bonds, with an adjacent empty or partially filled orbital. Okay, so it's a stabilizing interaction because of the CH bond or CC bond that are present next to this empty orbital. What it means is this empty p orbital will be stabilized in the presence of CH bond. So what's happening actually is the CH bond, which consists of sigma electrons, right? They are going to neutralize this positive charge by sort of like bringing some electron cloud into this periphery, right? That's hyperconjugation. So hyperconjugation is a stabilizing interaction, happens in case of carbocation and free radical, you can imagine, because in carbanion there is no free orbital, no empty orbital, right? The empty orbital is present in carbocation, the partially filled orbital is present in free radical, so hyperconjugation effect is only present in carbocation and free radical. And the way hyperconjugation helps in the stability of those free radical is by helping sort of suppress the positive charge with the sigma, carbon-carbon or carbon-hydrogen sigma electrons adjacent to the carbon center, the positive center. Okay, that's important. So that's structured, that's how it works, hyperconjugation. So that's the MTP orbital. These are CH electrons. So some of the CH electrons would sort of, dilute the positive charge. And diluting the positive charge means making it more stable. And hyperconjugation is also present in free radicals. So if there is free radical is sort of like a electron deficient species, right? It is an electron deficient species. It might not be as deficient as the carbocation, but still a electron deficient species. So if there is a free radical also, this CH bond is going to help overcome some of that deficiency and make the free radical more stable. Okay, so free radical is not, the hyperconjugation effect is not present in carbanion. It is only present in carbocation and free radicals. And in both those cases, hyperconjugation helps in stability of the carbocation and free radical. More the hyperconjugation, more is the stability. Okay. Now the second factor is inductive effect. Okay. Before getting into the definition, let me actually tell you something. So whenever you have a carbocation, carbanion, or free radical, around the positive center or a negative center or the unpaired electron center, there are either electron donating group like alkyl group, which are rich in electron. Alkyl groups are electron donating group, or there could be electron withdrawing group. If there is a really electron negative atom or a positive charge in the periphery of those center, that's gonna withdraw the electron from the positive center or a negative center or the unpaired electron center, right? And if the group is donating the electron to the carbon center, that's called positive inductive effect. If the group is withdrawing the electron from the center, it's called negative inductive effect. And depending on whether you are talking about carbocation, carbanion, or free radical, the positive inductive effect and negative inductive effect are going to change the stability of the carbocations, carbanions, or free radicals. Let's talk about carbocation first. Okay, so you have a positive center. If you are withdrawing electron from the positive center, you are making the positive center more positive. Okay, which means more reactive and less stable. So if there are electron withdrawing groups around the carbocation center, that's going to make the carbocation less stable. That's going to make the center more positive. But if there are electron donating group around the positive center, that's going to make the carbocation less reactive and more stable. For example, if there are alkyl groups around the carbocation, those alkyl groups are going to donate electron, okay, through the sigma bond. It's a different donation than the hyperconjugation. In the hyperconjugation, the donation was through the carbon-hydrogen sigma bond. It's through this carbon-carbon bond. So if there are electron donating groups like alkyl groups around the carbocation, those are going to make the carbocation more stable. And that is also one reason why the tertiary carbocation is more stable than the primary, because there are 3 alkyl groups and they are going to push the electron towards the positive center, making it less positive and more stable. Very, very similar to the hyperconjugation, right? In hyperconjugation, the alkyl groups were donating the electron through the CH bond. Here they are donating directly through the CC bond. But both hyperconjugation and the positive inductive effect are making the carbocation more stable. Now let's go to the carbanion, which is going to be a little bit different, right? Because if you see the trend, it's already different. So in carbanion, the more the electron donating group around the carbon, the more electron dense this negative carbon is going to become. That means it's going to be more reactive and less stable. So having more alkyl groups around the negative carbon center is going to make it less stable and more reactive. If there were electron withdrawing groups around that carbanion, that would have made it more stable, because that would have neutralized some of the negative charge. Now if you go to radicals, the free radicals, which are also electron deficient, that means they're very close to carbocation, and the trend is very similar. The more the electron donating group, the alkyl group around the free radical, the more stable the free radical is going to be, because they are going to be less electron deficient because of the donation from the alkyl group. That's why the tertiary alkyl group is much more stable than the methyl. Tertiary free radical is much more stable than the methyl free radical. Okay, so we talked about hyperconjugation, which was donation of CH electrons to the empty free orbital. Now, empty p orbital. Now in inductive effect, it's either donation or withdrawal of electron from the carbon center via the CC bond. Now let's talk about the third factor, which is the resonance effect, right? And let's do a little recap on what you know about resonance so far. You know, I guess you know that whenever there is a single bond and double bond in sort of like alternating position, then you can draw more than one possible structure for a molecule. And that's the phenomenon is called resonance. The structures are called resonance hybrid. The final structure is, no, the structures are called resonating structures. And the final structure is called resonance hybrid. And the process of resonance makes a molecule more stable, right? Yeah, and that's very true. And it's very similar in case of carbocations, carbanions, and free radical, right? So if you look at this carbocation, this is the carbon with a positive charge, and there is a double bond adjacent to the bond containing the carbocation, right? If you have situation like this, then you can draw a resonance structure for this. And the way you draw is, let me try this out, right? Let me try this out. So the way you draw is, so you can basically move these electrons here, because these are pi electron mobile. So as a result, you can draw a structure like this. So the double bonds are here and a positive charge has moved here. So these two are resonating structures. And if you look at this alkane, which looks similar, just the difference is there is no pi bond, you can't draw resonating structure for this. There is no resonance. That's why this alkane, this carbocation is more stable than this. And these types of carbocations are called allylic, A-L-L-Y-L-I-C, allylic carbocation. So allylic carbocations are more stable than the regular non-allylic counterparts. Okay, same here. So you can basically move these pi bonds here, and as a result, the new carbocation that we're going to get is, since you move the positive charge is going to come here and the pi bond has moved here. These two are resonating structures. Okay, but here there is no resonance structure. That's why this carbocation is more stable than similar looking this carbocation, which is not similar, because this is a regular carbocation, this is allylic, this is a secondary carbocation, let's say, and this is an allylic carbocation. Okay, same goes for free radicals. Here you can draw a resonance structure, here you can. You can move this pi bonds here. As a result, the new structure is going to look something like this. These two are resonating structure. That's why the allylic free radical is more stable than the primary free radical here. Let's talk about carbanion. Same here. You can't draw a resonance structure for this, but here you can. Now you can't move this double bond here because this is already electron rich. So what you can do is you can move this pair of electron here, and this double bond can go to this extreme carbon, the end carbon. As a result, the new structure is going to look like something like this. This is a negative charge on the side. This is a negative charge. I can't erase this, but okay. So that's the resonating structure for this. Now here, you can actually draw two resonance structure. One, you can move this here. Right? And this can look like, so resonance structure would be something like this. So there's a negative charge here, you move that lone pair here, and that's one. right? Or you could also move this here and bring this negative charge, bring this pi electron as a negative charge at the end carbon. So the whole idea is a resonance effect leads to a stabilization of molecule via the delocalization of mobile electrons. So whenever you have a positive carbocation, carbanion, or a free radical, and there is a double bond in the adjacent carbon-carbon bond, then there is the possibility of resonance, and that makes the carbocation, carbanion, and free radical all more stable, all, right? And this effect is possible only in case of allylic carbocation, allylic free radical, or allylic carbanion. Whenever you have this allylic species, then there is resonance possible, and in all this situation, the resonance makes the reactive intermediates more stable. Now we know the different factors that affect the stability of carbocation, carbanion, and free radicals. The three important factors: hyperconjugation, resonance stabilization, and the inductive effect. Let's do a little application, right, on the factors. So these are the four different sort of carbocation that we have learned previously, and also we talked briefly about the allylic carbocation, where you have a positively charged carbon center and a double bond adjacent to the bond, right? So, and we know the stability of carbocation varies this way. The methyl carbocation is the least stable, and the tertiary carbocation are the most stable. So what factors come into play while we talk about the stability of carbocation? First, hyperconjugation, because carbocation have empty p orbitals, and there's a CH bond most of the time next to the p orbital, so that CH bond can contribute to the delocalization or dilution of that positive charge, making the carbocation more stable. Higher the number of CH bonds, more substituted the carbocation, more stable the carbocation, right? More neutralization of the positive charge. So, and carbocation's stability is also affected by the inductive effect. If there are electron donating group like the alkyl group, which cause positive inductive effect, that would increase the stability of carbocation, because electron donating group would make that positive charge less positive. And that's also one reason why the tertiary carbocations are more stable than the methyl and the primary and the secondary, because there are more R groups, more positive inductive effect, right? But if there is a electron withdrawing group, something like a CF3 group, CF3 is a very electron withdrawing group that withdraws the electron from the carbon center, and it's going to make that carbon center more positive. That means it's going to make it less stable. So if you are to rank this guy in this group, you'll put it somewhere at the end. This is going to be even less stable than the methyl, because the positive charge is being magnified because of this CF3 electron withdrawing group. Okay, so just remember, alkyl groups are electron donating group. They make the carbocation more stable. So hyperconjugation, inductive effect, and also resonance stabilization is present in some carbocation, right? The allylic carbocation. We talked about this earlier. So whenever you have a positive charge and a pi bond in the alternate position, you can basically move the pi bond here and create this structure, which is basically the resonating structure. So presence of resonance makes the carbocation more stable. Same here. You can move this double bond here. Here also you can move this double bond here, but you can't do this for this two different carbocations. So this is more stable than this. This is more stable than this. Now let's see carbanions. We already know this trend. The methyl carbanion is the most stable. The tertiary carbanion is the most stable, least stable, sorry. And if we are trying to weigh in the factors that we talked about before, first, there is no hyperconjugation in carbanion, right? Because there is no empty p orbital. That's why you can't donate those CH bonds into this orbital. There is no empty p orbital. The p orbital is completely filled. So there is no hyperconjugation in carbanion. There is inductive effect, however, because there could be electron donating groups like alkyl groups, right? Or there could be electron withdrawing groups like the CF3 group we saw in carbocation. But the effect are going to be very different than the one for the carbocation. That is, if there are more electron donating group for carbanion, that's going to enhance the electron density on that center, making it less stable. If there are less electron donating groups, in the methyl group there are no electron donating groups, the negative charge won't be concentrated, right? It won't be enhanced. As a result, this will be more stable. Therefore, electron donating groups make carbanion less stable. Electron withdrawing group, however, would make the carbanion more stable. So if there was a CF3 group here, that would make this carbanion more stable. Okay, just the opposite to the effect that we saw in carbocation. And of course, the resonance stabilization is also present in carbanion, and those carbanions are called allylic. You can basically move this extra electron here and move this pi bond here and create a negative charge here. That's the resonating structure. You can do it, you can draw actually two more structures for this. You can either use this electron here. Let's try this again because I don't think we did a great job in the earlier. So what you can do is you can move this here and then move this here. As a result, let's try to draw it better this time. You can create pi bond here and a negative charge here. That's one. Other, you can also move this electron here and the pi bond here at the end. As a result, get the other resonating structure, which would look something like this and this. So these are all resonating structures. So this would be the more stable because it has three resonating structure. This would be the second more stable here because this has one more resonating structure. Let's draw that again because in the last one we didn't do a great job. So bring it here, bring it to the end carbon. As a result, you are going to get structured like this. Second most stable because there are two resonating structure. In this case, there are no resonating structure. So resonance, having resonance structure will also make carbanion more stable. So in carbanion, there is inductive effect and there is also resonance effect for allylic carbanion. Okay. Last but not the least, the free radicals. We know the stability whenever free radical go from methyl to primary to secondary to tertiary, their stability increases. And they are very similar to carbocation in nature because both carbocation and free radicals are electron deficient. Just remember that, okay? Free radicals are electron deficient because they want to have one more electron to complete that octet. They don't want to lose this electron. They want to gain one more. So the trend is very similar to the one for carbocation, okay? When you go from methyl to tertiary, the free radicals become more stable. And of course, the hyperconjugation is going to come into play. It's not going to be as strong as in case of carbocation because in carbocation, the p orbital in the positively charged carbon center was completely empty. In case of free radicals, it's going to be half filled, but still the CH bonds on the periphery can contribute to the stability of free radicals, right? It's not going to be as strong as in case of carbocation, but significant enough to talk about, right? So the more the number of alkyl groups around, the more is the contribution to the partially filled orbital and more is the stability. And that's also why, that's one reason why the tertiary free radicals were more stable than the other ones, right? And that's what I said earlier. Free radicals are electron deficient, so when you go from methyl to tertiary, they are going to become more and more stable. And what it talks here is inductive effect is relevant in free radicals, right? Of course, because if you have more electron donating groups around the unpaired electron, the more will be the stability. So the positive inductive effect makes the free radical more stable. But if there is electron withdrawing group like the CF3, it's going to make it less stable, right? Very similar to the carbocation trends. The positive inductive effect makes the free radical more stable. The negative inductive effect would make it less stable. And of course, the resonance stabilization is also present in case of allylic free radicals. So if you have something like this, you can always move this double bond here and have a unpaired electron here, which is this. So the possibility of resonating structures makes the allylic free radical more stable. That's why this free radical is more stable than the non-allylic counterpart. Okay, so that's basically it. Let's summarize the whole. We covered a lot today. So in carbocations, all factor hyperconjugation is always present except the methyl carbocation. The inductive effect depends on positive or negative. The positive inductive effect is going to stabilize the carbocation. The negative inductive effect would destabilize it. And the resonance stabilization might be present in case of allylic carbocation. They are present, right? And that makes the carbocation more stable. In case of carbanions, inductive effect is present if there are alkyl groups around. If the positive inductive effect would destabilize carbanion and negative inductive effect would stabilize opposite to the carbocation. Resonance stabilization might be present for allylic carbanion, but there is no hyperconjugation. Important thing, okay? Because the p orbital in the negatively charged carbon is completely filled, so there is no hyperconjugation. In free radical, inductive effect is present, of course. Positive inductive effect is going to stabilize the free radical. Negative inductive effect is going to destabilize. Very similar to carbocation. A resonance stabilization will also be present for allylic free radical. And hyperconjugation is also present, but it's less significant and pronounced in comparison to the carbocation. So yeah, I hope you guys now understand what hyperconjugation, inductive effect, and resonance stabilization are, and how these three different factors come into play while we talk about the stability of relative stability of different types of carbocations, carbanions, and free radicals. Okay, and thank you for listening, and I'll see you guys pretty soon. Thank you.